Good evening, Harshita.
Good evening, ma'am.
Am I audible?
Yes, ma'am.
Is your video off? I can't see you. Okay. No one is joined yet. Other trees are as trees now. Do you have any annual exams this time?
Yes, ma'am. It's going on.
Okay. Once again. Okay, can you see the video?
Yes, ma'am.
Is it clear?
Yes, ma'am.
Okay. Okay, we already late. So I think we should start now. The last class we already discussed about the effects, different type of impurities present in the solids, isn't it? That means the Schottky defect, Frankel defect, etc. Okay, and we also discussed about the P-type and N-type semiconductor. Okay, have you gone through the last portion?
I think last class I did not attend, ma'am.
Okay, are you absent on the last day?
Yes, ma'am.
Okay, okay, but we already completed the portion. That means the different type of impurities present in the solid state. Okay, I will. Okay, when after discussing with the Guruji team, I will again take the class. Okay, so today we are discussing about the magnetic properties of an atom. Okay, here each electron in an atom behaves like a tiny magnet. That means every substances will show some magnetic properties. Okay, each substances, how substances are made up of? They are made up of matter or any atoms, etc. Okay, and each atom is made up of electron, and this electron can behave like a tiny magnet. That means it can attract, it has some magnetic properties. Each electron in an atom can behave like a tiny magnet, and its magnetic moment originates from two types of motions. That means an electron can move two different ways. It can revolving around around its orbital motion around the nucleus, or otherwise, and the second type of motion is it can spin around its own axis. That means, have you learned in your social studies that how the planets revolving around the sun? Is it that it is an orbital motion? That means the electron is revolving around the nucleus. Here, electron is a planet and nucleus is the sun itself. So it will have an orbital motion. It will revolve around the nucleus. It gives give this orbital motion will give a magnetic moment to the electron. Another type of moment is it have a spin around its own axis. That means we know the Earth can rotate about its own axis, isn't it? Like that, the electron itself can rotate on its axis. So these two type of motions can make the electron to give a magnetic moment. Is my video clear? Any problem with the video?
Your video is not clear, ma'am. Like some
Okay.
green.
Okay, let me check. I think there may be any network issue. Okay, is my face clear?
Yes, ma'am.
Okay, I will again share the screen. Okay, I think the issue is with the PPT presentation. when I'm trying. Again, there is any problem in the video?
It is still the same.
Okay. Okay, can you read? Can you read from the PPT? Again, any problem?
No problem with PPT.
Is that unclear?
It's clear, ma'am.
Okay. So here in the diagram, you can see the first diagram will show how an electron is revolving around the nucleus. Can you see the diagram?
Yes, ma'am.
Okay, that is represented by A. Here the center point, here the central part is the atomic nucleus, and around this nucleus, this blue line gives the orbital motion of the electron. It is revolving around the nucleus. That means it has a permanent spin. Okay, that's why this revolving of electron around the nucleus make a permanent spin, a magnetic moment to an electron. Another one is, here you can see the electron itself has its own axis. So it can rotate about its axis. It also make a magnetic moment to the electron. Okay. And the revolving around the nucleus will give a permanent spin for the electron, and the rotation of electron about its axis give an orbital magnetic moment. These two are the reason for the magnetic properties of the electron. Okay, usually the magnitude of magnetic moment of an electron is a very small value. Okay, the unit of magnitude, the unit of magnetic moment can be written as Bohr magneton. That is, we can say it as mu b. Okay, mu beta or Bohr magneton. And one Bohr magneton or one mu b can be called as 9.27 into 10 raised to negative 24 angstrom meter square. Okay, you should note down the point as just the electron can act as a tiny magnet. It has its magnetic properties due to two type of motions like orbital motion around the nucleus and spin around its own axis. Okay, if you complete, just note me.
Yes, ma'am.
Okay. This picture is in your NCERT textbook itself. So I think you don't need to copy down. Just try to understand how it shows. Okay. Do you understand the diagram?
Yes, ma'am. Understood.
Okay. And this type of motions results the electron as a permanent spin and an orbital magnetic moment. It is very important topic. So this revolving and the rotation gives a permanent spin to the electron and also an orbital magnetic moment. Okay, these 2 points are very important. Also, note down the unit of magnetic moment as Bohr magneton. Okay. Have you completed?
Just a minute. Completed, ma'am.
Now, according to the magnetic properties of electrons, the whole substance can be classified into 5 types. That is paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic substances. Okay, there are 5 types of substances according to the magnetic nature of that substance, and they are paramagnetism, diamagnetism. These are the properties of substance. Okay, you should note down as paramagnetic substance, diamagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic. Okay.
Yes.
Okay. First of all, we can learn about paramagnetism. Have you, in my class itself, we have discussed this about the term paramagnetism. Have you remember? I think in the S block elements about the
Like we
ammoniated
have
electron. Have you remembered about the ammoniated electron, which impart a blue-violet color to the first group elements? Have you remembered about it? Paramagnetic and diamagnetic. When we discussed about the S block elements, that means lithium, sodium, potassium, when we discussed about the reaction of those first group elements or alkali metals with ammonia solution, we obtained an ammoniated electron, which give a blue-violet color solution. Have you remember about that term?
Yes, ma'am. Yes.
Okay, there we have discussed about this term paramagnetic. Okay, so here you can see the paramagnetism will get weakly attracted by a magnetic field. That means the substances which show paramagnetic property will only weakly attracted by a magnetic field. It shows its magnetic property due to the presence of one or more unpaired electrons. Okay, during paramagnetism, we have already discussed in that example that there will be one or more unpaired electrons. Okay, there will be some unpaired electrons. There will be some unpaired electrons after bonding, and due to its presence, there will be so the unpaired electrons can easily get attracted by the magnetic field. Okay, and after magnetization, these electrons will arrange in the same direction as that of the magnetic field. That means if we apply a magnetic field from one direction, the electrons will be aligned in the same direction from that of the magnetic field. Okay, and if we remove this magnetic field, this type of magnetism can easily lose their magnetic properties. Do you understand? If we place a magnet near a substance, it will get magnetized and the electrons present in those substance will be aligned in the same direction as that of the magnetic field. And it shows the magnetic property due to the presence of unpaired electrons. And if we remove this magnetic from the substance, it will again lose its magnetism. So that means it will act only as a temporary magnet. Okay, it does not have a permanent magnetic property. It shows its property only in the presence of a magnetic field. That is paramagnetic substances. The examples are oxygen, copper ion, iron 3+, and chromium 3+. These are the examples for the paramagnetic substances. Okay, so you should note down that only some points like presence of one or more unpaired electrons. Okay, it is the first feature of paramagnetism. So whenever you heard about the word paramagnetism, you should remember that there will be the presence of unpaired electrons. Okay, it is a very important point. And also, these paramagnetic substances lose their magnetism in the absence of magnetic field. That means it will act only as a temporary magnet. Third one is same direction of the magnetic field. The electrons will align or magnetize in the same direction of the magnetic field. These three are the main points in the paramagnetism, and you should also note down the examples. Okay, because you may get some questions like there will be some random ions, so you should randomly select which are the paramagnetic substances from that. Okay, so you should know which are the examples for paramagnetic substances. Have any doubt in this?
No, ma'am.
Can I move on to the next one?
Yes, ma'am.
Second type of substance is diamagnetic. It is the just reverse of paramagnetic. In paramagnetism, we learned that there will be the presence of unpaired electrons. Okay, but in diamagnetism, there will be no unpaired electrons. That means all the electrons will be paired. There is no unpaired electron. Each one will be paired. Their examples are water molecule, sodium chloride, and benzene. This C6H6 is benzene. This is the chemical formula of benzene. Okay. And these diamagnetic substances can be weakly magnetized in a magnetic field, and it will be in opposite direction. Okay. In paramagnetism, we learned that it will magnetize in the same direction as that of magnetic field. But in diamagnetism, it is magnetized in the opposite direction. Okay, it is the main difference in diamagnetism and paramagnetism. And these type of substances that all the electrons are paired, then there are no unpaired electrons. If there is no unpaired electrons, they cannot be get magnetized. Okay, that's why they said weakly magnetized in the magnetic field. So by pairing of electrons, each electrons, their magnetic moments can get cancelled. Have you learned how to write electronic configuration, the orbitals like 1s2, 2s2, 3s2, isn't it?
Yes, ma'am.
Okay, then have you learned about hybridization?
Yes, ma'am.
Okay, during that time you can see that that time you can see that the electrons are filled like this, isn't it? One spin up and other spin down, isn't it? So this is diamagnetic. No unpaired electron is there. Okay, can you understand? Here one electron has spin up and other one has spin down. So their magnetic moment will get cancelled, isn't it? But in paramagnetism, there will be one set of paired electron and another with the unpaired electron. Here you can see in the second column, there is an unpaired electron with spin up. It can be either spin up or spin down. Only one electron is there. There is this is unpaired one. That is why those substances, this is paramagnetic. Okay, those that why it shows some magnetic properties due to unpaired electron. But in diamagnetism, you can see there is no unpaired electron. They are all paired electrons. Okay, they are all pairing of electrons is there. And this, due to this pairing, their magnetic moments will get cancelled. Here you can see that. Okay, each electrons have spin up and spin down, so their magnetic moments will get cancelled. That's why they lose their magnetic character. Okay, do you understand the difference?
Yes, ma'am.
Have you completed this?
Completed.
Third type of substance is ferromagnetic substances. Ferromagnetic substances are attracted very strongly by a magnetic field. In the previous one, that is paramagnetic and diamagnetic, are weakly magnetized, but ferromagnetic substances can be strongly magnetized. The examples are iron, cobalt, nickel, gadolinium, and chromium dioxide. These are the best examples for ferromagnetic substances. Iron, in the daily life, we can see that iron, that is Fe, it is a magnetic, it has some magnetic properties, isn't it? We have learned about and we can see it from our daily life. Also, these ferromagnetic substances can be permanently magnetized. It is very important. Okay. Paramagnetic substances, the first one are temporarily magnetized. When we remove the magnetic field, it can lose its magnetic property. But in ferromagnetism, they can be permanently magnetized. That means if we place a magnetic field near this ferromagnetic substance, they can get magnetized, and even if we remove the magnetic field, they can sustain its magnetic properties. That means it can be permanently magnetized. Okay. Usually, in solid state, the metal ions of ferromagnetic substances are grouped together into small regions called domains. That means their electrons will be arranged in such a way to make a group of electrons. Okay, and this group of electrons can be known as domains. And each domain can act as a tiny magnet, because a domain is a pool of electrons and each electron can act as a magnet. So each domain can also act as a tiny magnet. Okay, here you can see the diagram of a ferromagnet, how the electrons are aligned in a ferromagnetic substance. Here you can see all the electrons are aligned in the spin up moment. Okay, each one is the electron. Each arrow mark represents electrons. Okay, each one is aligned with spin up moment. No spin down moments are there. Each one is spin up moments. And when the substance is placed in a magnetic field, all the domains get oriented in the direction of magnetic field and a strong magnetic effect can be produced. Okay, here each circle represents a domain. Okay, I can show you an example. If we have no magnetic field, that means in the absence of a magnetic field, in ferromagnetic substances, the electrons can be aligned in this way. There will be no definite direction. All electrons can be aligned in different way. Okay, but if we apply the magnetic field, what happen? If we apply magnetic field, all electrons will get aligned in the same direction. Okay, can you identify the difference? In the absence of magnetic field, the electrons will be aligned in different manner. They are randomly arranged. Okay, you can write it as absence of magnetic field. But in the presence of magnetic field, electrons can be arranged in the same alignment. All of them have same alignment. Do you understand? Have any doubts?
No, ma'am.
Okay. So this is how a ferromagnetic substance will show magnetic property and it acts as a permanent magnet. Okay. So you just note down this highlighted portion. It is a permanent magnet. Then example for ferromagnetism. Okay, have you completed?
Completed, ma'am.
So the second question you can see and you just draw this last picture. Okay, in the presence of magnet, it is in the presence of magnetic field how the domains are aligned. Okay, this ordering of domains will persist even when the magnetic field is removed. That's why the ferromagnetic substance can act as a permanent magnet. Okay, you have to think that in the absence of magnetic field, the electrons are aligned in random position. But by applying magnetic field, they are aligned in a particular direction. Okay, even when we remove the magnetic field, this alignment can persist. Okay, it can sustain the magnetic, so it can basically sustain the magnetic properties. Okay, can I move on to the next one?
Yes, ma'am.
Fourth type of substance is ferric antiferromagnetism. That is antiferromagnetic properties. Here you can see that the domains are, or otherwise the electrons are arranged in parallel but in opposite spin, isn't it? In ferromagnetism, you can see all have spin up, but in antiferromagnetism, some have spin up and some electron have spin down. Okay, also all are arranged in parallel. Okay, there is no random position. They are all arranged in random parallel position with opposite spins. Okay, so they have domain structure similar to ferromagnetic substance, but they are oppositely oriented and can easily cancel out each other's magnetic moment. Okay, so here there will it is a temporary magnet. There will be no magnetic property here because each electrons can cancel their magnetic properties. Why? Because some are spin up and some are spin down, isn't it? That's why the magnetic moment get cancelled. Do you understand?
Yes, ma'am.
Okay, you just copy down this diagram only. Okay, and also the example for
Good evening.
antiferromagnetic. Okay, good evening, Gopika. Here we are discussing about the magnetic properties of substances. Okay,
Yes, ma'am.
this is our fourth substance, antiferromagnetism. Okay,
Yes. Ma'am.
Have you remember that we discussed about the paramagnetic and diamagnetism in our last chapter? Like when we discussed about the S block elements, it's a reaction between the first group elements with ammoniated solution. We got ammoniated electrons with colored solution. Then we discussed about the term paramagnetism. Have you remembered that?
Yes, ma'am.
Okay, so here we discussing about the paramagnetism, diamagnetism, ferromagnetism, antiferromagnetism, and ferrimagnetism. Okay, this is the fourth type of substance. Okay, Ashna, you just note down the example for antiferromagnetism. Okay, and note down that domains are oppositely oriented and cancel out each other's magnetic moment. Okay. Have you understand the spin of these electrons, Harshada? How they are arranged?
Yes, ma'am.
Okay. Okay, can I move on to the next one?
Yes, ma'am.
The last type of substance is ferrimagnetism. Okay, here when the magnetic moments of the domains is the substance are aligned in parallel, like antiferromagnetism, but anti-parallel direction in unequal numbers. Here you can see in the diagram when we apply the magnetic field, some of the electrons are with spin up. Okay, how many spin up electrons are there? 1, 2, 3, 4. But only 2 electrons with spin down moment. Okay, so the electrons with same moment with same spin are unequal numbers, isn't it? In antiferromagnetism, you can see that same number of electrons with equal spins. Okay, but here some of the electrons have spin up moment, but their number will not be equal to the electrons with spin down. Okay, so that means the substances are aligned in parallel and anti-parallel direction in unequal numbers. And here they are weakly attracted by magnetic fields as compared to ferromagnetic substances. The strongest magnetic properties are shown by ferromagnetic substances because they can sustain its magnetic property even after we remove the magnetic field. Okay, but other 4 substances are weakly attracted by the magnetic field. Okay, then these substances lose ferromagnetic properties on heating and become paramagnetic. How is paramagnetic? The electrons are unpaired electrons will be there. And you also note down the examples for ferrimagnetism. Magnetite, ferrites, and zinc ferrite. These are the examples for ferrimagnetism. The examples are very important. Okay, you should note down the name and the chemical formula of these substances. Okay.
Yes, ma'am.
Harshada, do you have any doubt?
No, ma'am.
Okay, Gopika, this is our first portion. The electrons, this is the diagram same in your textbook. The electrons will have 2 type of motion. One is orbital motion, and there is the rotation about its own axis. Okay, here the central portion is the nucleus, and electron can revolve around the nucleus. And this revolving will give a permanent spin for the electron. And also the electron have its own axis, so it can rotate about its axis also. Okay, like Earth rotates about its own axis. So this rotation will give an orbital magnetic moment. These 2 type of motion will make an electron a magnet. Okay, it is due to this 2 type of motion, an electron can show some magnetic properties. And the unit of magnetic moment is Bohr magneton mu b. Okay, this was our first portion. And based on the magnetic properties, the substances can be classified into 5: paramagnetism, diamagnetism, ferromagnetism, antiferro, and ferrimagnetism. The paramagnetism as the name indicates, they are substances which contain 1 or more unpaired electrons. Okay, there will be some unpaired electrons, and due to this unpaired electron, they can easily get magnetized by applying a magnetic field. And if we remove the magnetic field, it will lose their magnetic properties. Okay, it is the specialty of the paramagnetism. It will lose its magnetism in the absence of magnetic field. And the examples is oxygen molecule, copper ion, iron, and chromium. Fe3 plus, okay, iron 3 plus and chromium 3 plus. These are the examples for paramagnetism. Okay. Second is diamagnetism. Here, opposite to the paramagnetism. Okay, there will be no unpaired electrons. All electrons is get paired. So they are arranged in the opposite direction of the magnetic field, and it also lose their magnetic property when we remove the magnetic field. And due to the pairing of electrons, their magnetic moments get easily cancelled. The examples are water molecule, sodium chloride, and benzene. Okay, have you completed?
Yes, ma'am.
The third one is ferromagnetism. They can be permanently magnetized. Okay, in a substance, in the absence of a magnetic field, the electrons will be randomly arranged, and the group of electrons can called as domain. And when we apply a magnetic field, these electrons will arranged in a particular manner. Okay, from the random position, they are getting arranged in the same alignment. And even if we remove the magnetic field, these ferromagnetic substances can be sustain their magnetic properties. So they are permanent magnets. Okay, the examples are iron, cobalt, nickel, etc.
Yes, ma'am.
Okay, here is the diagram for ferromagnetism. Here you can see here that in the absence of magnetic field, these electrons are arranged randomly. There is no particular direction. But in the presence of magnetic field, they are arranged in the special alignment. Okay, you can see this in this diagram. All are arranged in the same manner. Okay, that's all about the ferromagnetism.
Yes, ma'am.
And antiferromagnetism we already discussed. Okay, so here we completed the chapter of solid state. Okay, shall we do some problems from this chapter?
Yes, ma'am.
Okay, let's read the question. A metal crystallizes with a face-centered cubic lattice. Then the edge length of the unit cell is 408 picometer. What is the diameter of the metal atom? A metal crystallizes with a face-centered cubic lattice. So we got how the lattice is. It is FCC crystal. The edge length is given. What do you mean by the edge length? What is the parameter for edge length? A, isn't it? Small letter A. It is given as 408 picometer. We have to find out the diameter of the metal ion. Have you noted down the question?
Just a minute.
Noted.
Gobika completed?
Ma'am, no, ma'am.
Okay.
Yes, ma'am.
So in the question given that the crystal is an FCC crystal with edge length A, isn't it? A is equal to 408 picometer. Then have we already discussed about the packing efficiency of BCC, FCC, isn't it? So in that, do you remember about that? The packing efficiency in each type of crystals we discussed?
Yes, ma'am.
Okay. We have discussed about the relation between radius of the sphere and the edge length, isn't it? So
Yes.
how can you relate the edge length and radius of an FCC crystal? Have you noted down in your notebook from the last class? For FCC crystal, what is the relation between edge length and radius of the sphere or radius of the atom?
Radius of the sphere. B is
That
equal
means
to-
the sphere is the constituent particle or atom or ion, anyone. Okay. So have we noted down how the relation between the edge length and radius A and R in FCC crystal?
2 root 2 R.
Yeah, it's 2 root 2 R. Harshada, have you remember? Don't you the when we discussed about the packing efficiency? Are you absent?
No, no, ma'am.
Okay,
I did not attend to.
okay. Okay, I think there was some network issues for 2 days. Okay.
Yeah.
So for FCC crystal, the edge length and the radius of the constituent, the radius of the atom are related with the equation A is equal to 2 root 2 R. So here we have got the A, isn't it? 408. So we can easily find out the value of R, isn't it?
Yes, ma'am.
Okay. Do you understand the relation?
Yes, ma'am.
Okay. So you just substitute the values. No need to write down the answer now. From here, the question is to find out the diameter, isn't it? To find the diameter. Here we get the R radius only. Okay. So for diameter, what will be the answer? It will be
2 into
2R. Okay. So the answer is 2 into 408 by 2 root 2. From this, you can easily find out it. Okay. Do you understand how to find out?
Yes, ma'am.
Will be any doubt?
No, ma'am, no doubt.
Okay. Have you completed the substitution?
No, ma'am.
Okay. Harshada, I think if you're absent, there will be some difficulty to understand this portion. Okay, you just go through your textbook. There is a proof for how to find out the packing efficiency of different type of crystals. Okay, there we got the relation here, the edge length of each crystal and the radius of the atom. Okay, for FCC crystal, it is the relation. For body centered cubic center, there is another relation. Okay, we will go through the next problem. Okay, then you will understand it. Okay, can I move on to the next question?
Yes, ma'am.
So after substituting, we will get the answer as 288 picometer. Okay.
Yes, ma'am.
The next question is lithium form is the same type of question. Lithium forms BCC structures, body centered cubic structure. The length of the side of its unit cell is 351 picometer. Then find out the atomic radius. Okay. Here the question is lithium forms a BCC structure or body centered cubic structure. Then length of the side of each unit cell, that means again the edge length A is given as 351 picometer. Then we have to find out the atomic radius. Have you completed the question?
Yes, ma'am.
Yes, ma'am.
Okay. Here also, for BCC structure, the question itself, it is given that the crystal have a BCC structure and the edge length A is given as what? 351 picometer. Okay. Then what's the relation between, we have to find out the radius of lithium atom. Okay. Then what is the relation between the edge length A and R?
2R.
2R? It is the diameter. 2R is the diameter. For BCC structure, what is the relation
4 by
between?
root 3.
Yeah, it is equal to 4 by root 3 R. Okay. So here also by substituting the value for A, we can get that 351 into root 3 by 4 as R. Okay. So here also we can easily calculate the value of R for the lithium. Okay, it's a simple question, isn't it? All you have to know about the relation of edge length and radius. Okay. So you have to by heart it for the three type of crystals, what is their relation. Okay.
Yes.
Can I move on to the next one?
Yes, ma'am.
So the final answer will be 152 picometer. Okay, you have to check it out. Next one. Which of the following statements, you don't need to copy down this question. Okay, just read it. Which of the following statements about the interstitial compounds is incorrect? Haven't we learned about the different type of impurities or different type of effects? Gopika, do you remember?
Ma'am.
Do you remember about different type of impurities? In the last class, we discussed about it. Frankel defect, Schottky defect, vacancy defect.
Yes, ma'am.
Okay. So there we have discussed about interstitial defects. Okay. I will remember about it.
Yes, ma'am.
Okay. Here they said that the four statements are given and we have to check out which one is incorrect about interstitial compounds. They are much harder than the pure metal. They have higher melting points than the pure metal. They can retain the metallic conductivity and they are chemically reactive. From this four, we have to find out which one is the incorrect one. Okay.
Yes, ma'am.
Here there is a statement that we have a clue that the interstitial compounds are chemically inert as the impurity ions are present in the interstitial sites. Isn't it? From the name itself, we can see that in the interstitial compounds, the impurities are present at the interstitial sites only. Okay. So it have no effect with the other atoms. So these compounds are chemically inert. Okay, is the fact about the interstitial compounds. Then which one will be the wrong statement in the options? Which one can be the wrong one?
Second one, ma'am.
Isn't second one? Have you read out the statement? The last statement is the important point. The interstitial compounds are, can you see this box? This, is that clear? Can you see the box in the video? The interstitial compounds are chemically inert as the impurity ions are present in the interstitial sites. Can you read the box? Can you see this in my
Yes,
video?
ma'am. Yes, ma'am. No one.
Okay. It is a fact about the interstitial compounds. Okay. In the statement, they said that the interstitial compounds are chemically inert because the impurity ions are present in the interstitial sites. Okay. So when the impurities are present in the interstitial sites, they have no effect with the other atoms. Okay, that means they are chemically inert. What do you mean by inert? They cannot react with others, isn't it? That's the
Yes,
name
ma'am.
indicates inert. So among these
Option
four,
B.
which one will be the wrong one?
Option last.
Yeah, option 4, they are chemically reactive. It is the wrong statement about the interstitial compounds. Okay, so you don't copy down, you don't need to copy down this question, just point out this box only. The interstitial compounds are chemically inert because the impurity ions are present in interstitial sites. Okay, you just need to copy down this box only. Have you completed? Can I move on to the next question?
Yes, ma'am.
Yes, ma'am.
Again, if A is the length of the side of a cube, the distance between body-centered atom and one corner atom in the cube will be. Okay, if A is the length of the side of a cube, distance between a BCC atom and one corner atom in the cube will be. How can we find out the answer? Again, we have to find out the we have to check out about the packing efficiency portion. Okay, in the question it is given that A is the edge length. Then we have to find out the distance between what is a body-centered atom. The atoms will be present at the each corners and also at the center of the cube. Okay, center of the body, isn't it? That is body-centered cubic center. Okay, isn't it?
Yes.
Have any doubt in body-centered atom?
No, ma'am.
Okay, so we have to find out the distance between corner atom and the atom present at the body center. Okay. Have you completed this question?
Yes, ma'am.
Give 1 second. Okay, have you remembered the packing efficiency in BCC structure?
Yes, ma'am.
Here we have F, C, and A. Okay, you can see the edge F and the corner A. In the question, it is given that one atom is present at the corner and the other at the center. So we have to find out the distance between these two atoms. Okay, do you understand it? So we have to find out this length. Okay, so for BCC structures, the radius and edge length have a relation with A is equal to 4 by root 3 R. Okay, so here the B, that is the phase diagonal. B is, can you see the B and C?
Yes, ma'am.
Here B is the phase diagonal and C is the body diagonal. Okay, for phase diagonal, it is, you can see that it is B is equal to root 2A. We have already proved it in that question. Okay, B is equal to root 2A, that is the phase diagonal. And C, what is C? It is a body diagonal. Okay, it is the diagonal is passing through the body of the unit cell, center of the unit cell, in which the body center atom is present. So B is equal to root 2A and C is equal to root 3A. So here, what will be the half of the body diagonal? One atom is present at the corner and other at the center. Okay, so the whole body diagonal is not required, or we just need the half of the diagonal. Okay, so we can get half of the body diagonal as root 3 by 2A, isn't it? Body diagonal is root 3AC. So half of the body diagonal means it is root 3 by 2A. Okay, so this half of the body diagonal will give the distance between the corner atom and the central atom. Do you understand?
Yes.
The distance between corner atom and the central atom will give the half of the body diagonal. The body diagonal is given by the term C, which is equal to root 3A. So half of the diagonal means it is root 3 by 2A. Okay. So for that, we have to keep this picture in your mind. Okay. Do you understand?
Yes, ma'am.
Okay. Again, there's another question. The vacant space in BCC lattice unit cell. How can we find out the vacant space in BCC lattice? We know the packing efficiency of each type of cell. Okay.
Yes, ma'am.
So from that, we can just calculate the vacant space. What is the packing efficiency of BCC structure? Have you remember it? The packing efficiency of BCC structure?
Volume of one atom by volume of cube unit cell.
Yeah, we already proved it and we got a numerical value, something X percentage. Have you remember it? Out of 100, what's the percentage of packing efficiency in BCC? We have wrote it down there. Which is the most efficient?
68%.
Yeah, 68%. For BCC, the packing efficiency is 68. So from that, we can easily find out the vacant space. How can we find out? Just subtract the packing
Minus
efficiency from 100. Okay, 100
Yes,
minus
ma'am.
68. So what the answer will be 32. Okay, it's a simple question, isn't it? You just understand what the question is. Okay.
Yes, ma'am.
Again, another question. Which type of defect has presence of cations in the interstitial sites? Which type of defect has the presence of cations in the interstitial site. Is it metal deficiency defect, Schottky defect, vacancy defect, or Frenkel defect? Which one can be the defect with presence of cation in interstitial site? It is Frenkel defect. Have you remember the Frenkel defect? There are some cations are missing from its original position and they are placed in some interstitial sites, isn't it? That's why.
Yes, ma'am.
So the cations are present in the interstitial sites. That means the defect is Frenkel defect. Okay.
Yes, ma'am.
Okay, another one is you have to note down the question. Which one among these substances is extensively used as a piezoelectric material? Piezoelectric material. Piezoelectric. Which among these substances are used as a piezoelectric material? The option it is given that quartz, amorphous silica, tridymite, and mica. The answer is quartz. Just note down what is piezoelectric materials. Okay, these materials are those which produces electric current when they are placed under a mechanical stress. That means we apply some pressure or we apply some stress on that substances. They can produce some electrical current that are known as piezoelectric substances. And the example is quartz. It is used as the type of material because it can produce electricity when any mechanical stress is applied on it. Okay, so you should note down what is a piezoelectric material and the example for those type of material. Okay. Have you completed?
Yes, ma'am.
So this was all about the solid state. So we completed the chapter solid state. Okay. Now we have to start out a new chapter, solutions. So in the first chapter, we all discussed about the solid state, different type of solids, how about the arrangement. Okay. The second type is solutions. Have you learned about solutions in your high school section? Have you learned about solutions? Can you see the video? Is it clear?
Yes, ma'am.
Okay. So solutions can be in your atmosphere. There are. Can you name an example for solutions from our daily life? Gobika, can you give me some examples for? Okay, what is a solution? Is it a
Solute plus
liquid?
solvent is equal to solution.
It's not clear.
Ma'am, solute plus solvent is equal to solution.
Yeah, it's a solute plus solvent. Okay, can you give me an example?
Salt water.
Salt and water. Okay, Harshada, can you give me another example?
Lime water.
Okay, lime water. So here both of you an example with a mixture of liquid and salt, liquid or solid. Okay, that means salt mixed with water, so salt water, and lime mixed with water, lime water. Is only water can be known as solution. Only water mixture can be known as the solution. Can't gas be a solution? Okay, in the atmosphere, the all oxygen, nitrogen, helium, hydrogen, all these gases are mixture. Okay, and these also are other examples for solutions. That means solute plus solvent gives a solution. So this solvent or solute can be solid, liquid or gases. Okay, so only liquid forms cannot be solutions. Either a mixture of gases, mixture of liquids or mixture of solids can be also solutions. Okay. So solutions are homogeneous mixtures of two or more than two components. There can be in gases, liquids, or solids. Okay, so they are homogeneous mixtures with two or more than two components. And the two components in this solutions are, one is solvent, other one is solute. Solvent is the substance with largest quantity. Okay, it determines the physical state in which the solution exists. In the first example you given, it is the salt water. Gobika give an example of salt water.
Yes.
Then which one is the solvent? The in salt water, which is the solvent?
Water, ma'am.
Water is the solvent. Why water is the solvent? How can you distinguish water as name water as solvent?
And the water only will dissolve.
Yeah, the
salt.
solute is dissolved. So the substance that can dissolve in larger quantity. Solvent here, water is the larger quantity. So it is the solvent that can get diluted in it. Okay. So salt is a very minimum quantity. It's the solute, and solute can dissolve in larger quantity of substance, and that larger quantity is known as the solvent. Okay. Do you understand the difference between solute and solvent?
Yes, ma'am.
Solute can be one or more components. If we make lime water, Harshada, which are the components present in lime water?
Lime and water.
Only lime and water? Can you drink only lime and water?
Sugar.
Sugar.
Yeah. Can you drink it without salt or sugar? No, isn't it? So we have three components there: lime, sugar or salt, and water, isn't it? So there are three components there. Again, which is the solvent present in the lime water? Which is the solvent?
Yeah.
Water is the solvent because we mix this sugar and lime in water. It is the larger quantities component. And which are the solutes present in lime water? Which are the solutes?
And sugar.
Sugar and lime. So in that example, we have two solutes. Okay, can you identify the difference? Solute can be one or more components present other than the solvent, and solvent is the largest quantity. And by determining the physical state of the solvent, we can determine the physical state of the solution also. In lime water, what is the physical state of lime water? It's a liquid form, isn't it? Because in that the solvent is a water. Water is in a liquid. So the whole solution have a liquid structure. Okay. So it is the nature of solvent which determines the physical state of a solution. Okay. Then for another example, atmospheric, when there is an atmospheric smog. Okay. SMOG, not smog. Have you seen smog in the highly polluted areas like Delhi, New Delhi? We have come across some news about New Delhi in our daily life.
Yes,
Okay. Because in New Delhi, there is air pollution which contain sulfur gas and carbon dioxide, any other substances. Okay. Here, the atmospheric air is the solvent. Okay. It's a gaseous form. And other polluted substances are also gases. Sulfur dioxide, carbon dioxide, these are also gases. Okay, that smog is also an example for solution. Okay, so the solvent also is a gas, solute also is a gas. Okay, so that in the atmospheric pollution, the smog present solvent as a gas. Since the solvent is in gaseous phase, the whole solution also have a gaseous phase. Okay, so it is the solvent which determines the physical state of a solution. Then let's see what is a binary solution. By the name binary, it contains two components. Here the salt water. Salt water contains only two components, salt and water. So it's an example for binary solution. Okay, but lime water, it's not an example for binary because there is three components: water, sugar, and lime. So there are three components. So that's not an example for binary solution. Okay, that's the first intro part of solution. Let's see different type of solutions. Okay, I have already said there are gaseous solution, liquid solutions, and solid solutions. And in gaseous solutions, the the solvent will be gas. Okay, the solvent can be gas. That why the whole substance is gaseous state. Can you understand what I said?
Sure.
Have any doubt, Harshada?
Can you come again?
Okay, for gaseous solutions, the solvent will be a gas. Have I told you the example of air pollution in New Delhi? Okay, the atmospheric air, the atmospheric oxygen or atmospheric air is the solvent. It is in the gaseous form. Okay, the other pollutant air molecules, that means sulfur dioxide, carbon dioxide, they are also at the gaseous form. Okay, so the substance in which this solute is dissolved is the solvent. And if the solvent is in the gaseous form, then the whole solution will be in the gaseous form. Okay, it is the solvent which determines the physical state of the solution. Okay, so by the name indicates, for gaseous solution, the solvent always will be a gas. Okay, then what about liquid solutions? The solvent will be a liquid. As you said, lime water. It's an example for liquid solution because the solvent is water, it's a liquid form. Okay, so it is liquid solution. Then what about solid solution? Well, for solid solution, the solvent will be solid. Okay, like when we mix the iron powder. Have you seen some iron powder from the sand? Have you
Yes,
played with iron powder from the sand in your childhood? By using magnet, you can easily get some iron powder from the sand that we used for building material. Okay, have you seen it?
Yes, ma'am.
Okay, so if you mix some, okay, then the sand itself, it may contain some other particles, iron fillings, etc. Okay, so the sand itself is a solid. So it is also an example for solid solution. Okay, do you understand the difference between these three?
Ma'am.
Yes, ma'am.
Okay, so first one, here you can see the example for gaseous solution. If the gas solvent, if the solute also is a gas, the example is mixture of oxygen and nitrogen. In the atmosphere, you can see the different type of gases are present, like hydrogen, helium, oxygen, nitrogen, carbon dioxide, carbon monoxide. These all are gases. Okay, so the gases are present or dissolved in the gas itself. It's the first example. Then second one is liquid. The example is chloroform mixed with nitrogen gas. Here nitrogen gas is the solvent and chloroform is a liquid form. Have you go through the chloroform in your chemistry lab? Have you seen it? No, okay. Have you
No,
seen
ma'am.
chloroform in the films or any other social media? Haven't you seen chloroform bottle in the films when the villain try to make trap with other girls or other ones, use chloroform to mask chloroform to.
Yes, ma'am. Yes, ma'am.
Okay, have you seen any part of this in any films?
Yes, ma'am.
Okay, it's a liquid form. When we smell the chloroform, we will get hangover. Okay, that's the specialty of chloroform. So this chloroform is mixed with nitrogen gas. It's an example for liquid solute in the gaseous solvent. Then have you seen through camphor? When
Yes,
you're
ma'am.
praying, you use camphor daily. Okay, so camphor is a solid. It's a solute here. And when it mixed with nitrogen gas, it is also an example for the gaseous solution. Okay, so you just know you have to thoroughly learn this table. Okay, it is in your NCERT textbook itself. So you should learn difference between these three solutions, that is gaseous, liquid and solid. What is the main difference? Each solutions determine how they are solvent. From the name itself, you can see that which type of solvent is present. For gaseous solution, the solvent is gas. For liquid solution, the solvent is liquid. For solid solution, the solvent is solid. Okay, first of all, you have to know what is a solute and what is a solvent. Okay, have any doubts?
No, ma'am.
Harshada, do you understand what is solvent and different type of solutions?
Yes, ma'am.
Okay, can I move on to the next one?
Yes,
ma'am.
ma'am.
So, in solutions, we have to calculate the concentration of solution. What do you mean by concentration? Then, for example, in the salt water, if you add just 1 teaspoon of salt to the water, okay, by adjustment we can drink it, okay. But if we add 5 or more teaspoon of salt, how can be the solution? Can you drink it? To 1 glass of water, if you add 5 or more teaspoon of salt, can you drink that water? That salt water?
No, ma'am.
No, ma'am. No, sorry. So that here the concentration or the quantity of solute is very much higher, isn't it? When we add so much solute to the solvent, the concentration of the whole solution will get increased. Okay, that means according to the quantity of solute, the concentration of the solution will get affected. So for each solution, we have to calculate the concentration of the solution. That means how much solute is present in the solution. For that, we have seven methods to calculate the concentration of solutions. They are mass percentage, volume percentage, mass by volume percentage, parts per million, mole fraction, molarity, and molarity. Okay, we can calculate the concentration of solution by 7 methods. First one is mass percentage. We can express it by W by W, that is mass of component in the solution divided by total mass of solution into 100. That is mass percentage. Okay, in the salt water itself, if we take just 1 gram of salt, here you can apply the equation as 2 divided by total mass of solution can be 10 milligram of water, 10 milligram of solution. Okay, so we can get 2 by 10 into 100. Okay, so mass of component in solution divided by total mass of the solution into 100. That gives the equation for mass percentage. Usually we calculate the concentration of solution by this method in the industrial applications. Okay.
Yes, ma'am.
Second one is volume percentage. The first one we use the mass of component as the name indicates. The second equation we use volume percentage. That means volume of the component. That how much percentage or how much milliliter volume of the component is using. Volume of component divided by total volume of the solution into 100. That gives the volume percentage. V by V. Third one is mass by volume. That means mass of solute divided by volume of solution. Okay, from the name itself, you can write down the equation. Isn't it easy? For mass percentage, we use the mass of solute and mass of solution. For volume percentage, we use volume of solute divided by total volume of solution. For mass by volume, there will be mass of solute divided by volume of solution. Okay, it's easy to find out from the name itself. Okay. Then this equation is using in the pharmaceutical or medical field. Okay. Fourth equation is parts per million, ppm. That means if the concentration is very minute or to the very minute amount of solute is present, we can calculate the concentration in the terms in ppm, that is parts per million. That is number of parts of component divided by total number of parts of all components. Okay. Into 10 raised to 6, that is parts per million. Have you completed this table?
Yes, ma'am.
Fifth one is mole fraction. Have any doubt, Gobika?
No, ma'am. Here.
Fifth one is mole fraction. That is the number of moles of component divided by total number of moles of all components. Okay, that means we have to find out the number of moles first. Here is the equation for binary solution. What is binary solution? So will be 2 components only. Okay, that is binary solution. So for binary solution, the mole fraction can be written as XA is equal to number of moles of A divided by total number of moles of all components, which are the A and B are the components in binary solution. So Na is the number of moles of A and Nb is the number of moles of B, component B. So for binary solution, we can write the mole fraction XA as Na divided by Na plus Nb. Then how can be the mole fraction of B? Can you write down the equation for the mole fraction of component B? Harshada?
N divided by
Yeah, Nb divided by say
Na plus
denominator
N.
Na plus Nb. So do you understand how to write down the equation? Okay, it is in the term of binary solution. Then what will be it in the case of other, if there are two or more components, how can you write the equation? We can write it as Ni divided by sigma Ni, that is total number of moles of whole components will be there. That is, we can write it as Ni divided by, if there are 10 Z number of moles, N1 plus, N2 plus, N3 plus up to Nz. Okay. How many components there? That much of total number of moles of whole components. Okay. Do you understand?
Yes, ma'am.
Yes, ma'am.
Then the sum of all mole fractions will be 1. That is the mole fraction of each components. That is XA plus XB plus XC, etc., will be equal to 1. If we sum up, if we total the mole fraction of all components, we will get the answer as 1. Okay. Do you understand?
Yes, ma'am.
The next equation is molarity. This molarity and molarity will get confused. So you just note down it thoroughly. It's very important. Most of the questions we use these two equations. Okay. Molarity. You have to note down the spelling also. For molarity, we represent molarity as capital M. Okay. The equation is moles of solute, number of moles of solute divided by volume of solution in liter. Okay. Number of moles of solute divided by volume of solution in liter. That is molarity, capital M. You have to note on especially for molarity, the expression is capital M, and the equation is mass of solute divided by volume of solution in liters. It is very important. Okay.
Yes, ma'am.
It's very important one. The next is molality. From the name we can get a clue that little. So the term will be little m, smaller term. Okay, that is for molality. And the same equation is moles of solute divided by mass of solvent in kilogram. Okay. For molality, smaller term m, the equation is moles of solute divided by mass of solvent in kilogram. For capital M molarity, the equation is moles of solute divided by volume of solution. Okay, total volume of solution. But for smaller term molality, moles of solute divided by mass of solvent only in kilogram. Okay. Do you understand?
Yes, ma'am.
Have you completed this?
Yes, ma'am.
Yes, ma'am.
Okay. So can we do a problem from this portion? You just note down the first problem. Calculate. Okay, don't you just know the second question. Okay, second one. Calculate the molarity of each of the following solutions. 30 gram of CuNO3 twice cobalt nitrate .6 H2O in 4.3 liter of solution. Okay, note down the second question. Calculate the molarity of 30 gram of cobalt nitrate .6 H2O in 4.3 liter of solution. Have you completed the question? There are two sub questions are there. Okay, 30 gram of cobalt nitrate in 4.3 liter, and the second question is 30 ml of 0.5 molar H2SO4 diluted in 500 ml. There are two sub questions there. Okay. Have you completed the question?
Yes, ma'am.
So here we have to find out what is the question? We have to find out the molarity.
Molarity.
Okay, that is capital M, isn't it? So what is the equation for molarity?
Moles of solute by volume of solute method.
Yeah, moles of solute divided by volume of solution into, do we have into 100? No, there was no into 100. Okay. Okay, so here we have to find out number of moles of solute and the volume is given, isn't it? Volume of the solution is given. What is the volume? Given in the question. What is the volume given?
4.3 moles.
Yeah, it is 4.3 liter. We are doing the first subdivision. Okay, we have to find out the molarity of cobalt nitrate. Okay, so M molarity of cobalt nitrate CO NO3 twice dot 6H2O. Isn't it the chemical formula? So
Yes,
we
ma'am.
have to find out the molarity. For that, we have to find out the number of moles of solute first, isn't it? The number of moles is not given in the question. Okay, which is the solute here in the solution? Which is the solute? This cobalt nitrate is the solute. Okay, so we have to find out the number of moles of cobalt nitrate. How can you find out the number of moles? What is the equation to find out the number of moles? I think you already learned this in the previous classes. Have you remember?
Mass of solute by molecular mass.
Yeah, mass given divided by molecular mass, isn't it? Arshada, have you remember this equation? In the earlier classes, you have already learned this. Number of moles can be calculated by the equation mass given divided by molecular mass. Mass given is, what is the mass given? Which, how many grams of
30.
cobalt nitrate is there?
30
Yeah, 30 grams is there. Then what is the molecular mass? It is not directly given in the question, but you have to calculate the molecular mass. Okay, so for that we have to calculate the mass of cobalt, nitrogen, 3 oxygen as there. Okay, O nitrogen, hydrogen. Okay, how many elements are there? Cobalt, nitrogen, oxygen, hydrogen. How many cobalt is there? 1 cobalt.
1.
Then how many nitrogen? 2 nitrogen atoms. And how many oxygen atoms are there?
6.
Only 6. There is a water molecules also. 6H2 is also there.
18. Sorry, miss,
12.
How many
12.
oxygen
12,
molecules?
ma'am. 12.
Yeah, it's 12 oxygen molecules and 6 hydrogen molecules. Okay, so you have to find out the molecular mass of the cobalt nitrate. I will give you the final answer as it is 310.7. That will be the molecular mass of this compound. Okay, it is 310.7. Okay, from this you can find out the number of moles. Okay,
Yes, ma'am.
okay, I think the answer will be 0.0966. Okay, that is the number of moles. Then from this we can calculate the molarity capital M for the cobalt nitrate. Okay, that is 0.0966 divided by the volume is given as 4.3. Okay, that's how we can find out the molarity of the given substance. Do you understand how to calculate?
Yes, ma'am.
Okay, so in some questions the molecular mass will not be given, so we have to find it out. Okay, then what is the second question? 30 ml of 0.5 molar H2SO4 to 500 milliliter of water. It is in the question. Have you noted down that from the question?
Yes, ma'am.
Okay, in the question it is given that 30 ml of 0.5 molar H2SO4. Isn't it? That means the molar is already given as 0.5. Concentration of sulfuric acid H2SO4 is already given as 0.5. It is diluted to 500 milliliter. That is the volume of solution is 500 milliliter. Okay, so we have to find out the molarity of 30 ml of 0.5 molar H2SO4. Okay. In the question, you can read that 0.5 molar H2SO4 is given. That means 1000 milliliter of 0.5 molar H2SO4 can contain 0.5 moles of H2SO4. Okay, I can write it as 1 liter, that is 1000 milliliter of 0.5 molar H2SO4 can give, or it contains 0.5 moles of H2SO4. That means 0.5 moles of H2SO4 are present in 1000 milliliter. We have to find the moles in 30 milliliter. Okay. In the question, it is given that we have to find the molarity of 30 ml of 0.5 molar H2SO4 diluted to 500 ml. Okay. So, in the question, we can identify that 1000 ml of 0.5 molar H2SO4 can contain 0.5 moles of H2SO4. Okay. So, how much moles in 30 ml will be there? In 30 ml, it can be 0.5 divided by 1000 into 30. Isn't it? It's the basic
Yes,
mathematics.
ma'am.
Do you understand how to calculate? 1000 ml, we have 0.5 moles. Then in 30 ml, it is 0.5 by 1000 into 100. Okay.
Yes.
What will be the answer? What's the answer for this? 0.5 divided by 1000 into 100 is 0.15. Have you got the same answer? Both of you got the same answer?
Yes,
Yes,
ma'am.
Okay. So here we got the number of moles in 30 ml. Now we have to calculate the molarity, capital M, as number of moles divided by volume of solution. Isn't it? We have to find out the molarity of 30 ml of H2SO4. That's why we have to separately find out the number of moles present in 30 ml. Do you understand the question? Okay, can you understand the question? Why we are separately calculating the number of moles for 30 ml only?
Yes, ma'am.
Okay, so for 30 ml, we got the number of moles as 0.015. And the question is given that this 0.5 molar H2SO4 is diluted to 500 milliliter. Okay, isn't it? In the equation of molarity, we learned that the equation with number of moles divided by volume of solution in liters, isn't it? In the question, it is given that 500 milliliter. Okay, then we have to convert this 500 milliliter into liter. Okay, how much 500 milliliter is, how much liter is there? 0.5 liter, isn't it? So you have to note down this term also, liter, in the equation. Okay, so in the equation we can got it as 0.015 divided by 0.5. Okay, do you understand? The answer will be 0.03 molar. Okay, do you understand how to calculate this?
Yes, ma'am.
Okay, any doubt in this question?
No, ma'am. No doubt, ma'am.
Both of you understand?
Yes, ma'am.
yes, ma'am.
So today's class we discussed about different solutions and what is a solution, different type of solutions, examples for solutions, and how to calculate the concentration of solutions. Okay, among this, molarity and molarity is the most important equations. You have to thoroughly learn the equations also and the expression, how to express the term. Okay, there are too many other questions. We can discuss it in the other class. Okay, thank you.
Yes, ma'am. Thank you, ma'am.
Thank you.
Thank you, ma'am.